All right, I think we're up and running. Says we're recording. So in this video, we're going to talk about some of the newer problems for the second half of the term. I'm going to put a sinusoid up on the board and make just a couple of comments about it. We're going to start looking at how to find the center and radius of circles, bounded area, how to draw it, algebraic fractions. Kind of wish we'd done a lot of that, or you'd done a lot of that in your Algebra 1, but we got to do a lot of work here. Compound interest and evaluating sine and cosine unit circle ratios. That's not new, but we got to do it every day. All right, so a couple of comments about this sinusoid. I think the question you'll see on the worksheet, day one, is the range. You want to find the range, about as easy as it comes. You know, sinusoids go up, go down, go up, go down, so on and so forth. The question is, what are the numbers over here? All right, 9 is the center, 7 is the amplitude. So what's the range? Those are y values. And those y values are less than or equal to 16 and greater than or equal to 2. I'm not going to spend much time on that. Don't have to learn it immediately, but after you see it 2 or 3 times, you should probably have that without too much trouble. Understanding why we're getting it, that's the issue. So here's the major function, and it's got an inside part. And that's what I'd like you to pause the video for a second and think about that inside part. What's it stand for? What unit of measurement? And now I've been saying it right along for a couple of weeks. That doesn't mean you processed it yet. Okay, so one more time. What's it represent? I can almost hear some of you saying angles, and you're absolutely right. But there's no degree symbols here. So therefore, we're looking at what? Radian measurements, radius lengths. And where do they start in this particular part? Well, our eyes are glued to the number 20. And if I put the number 20, my angle is 0 radians. What's 0 radians? No walk around the circumference of the circle. Not walking around the circumference of the circle. How about I put a 25 in, because it sure looks like multiples of 5 would be user-friendly. Well, I put a 25 in that parentheses, I'm getting 1. Ah, 1 radius length. Right about there. Yeah. And if I put the number 30 in, I get 2 radius lengths, twice that length. Right about there. And if I get 35 in here, 15 divided by 3 radius lengths. That looks about right to me. And that forms the top half of a circle. What are we doing when we draw these little circumference measurements? We then slap some triangles in here. Let's do one right at 1. That angle, 1 radius length. That's a smaller one, right? That's a small, but it's the same ratios. So what do we have? Well, I've been asking you to memorize that 1 radian is about 57.3 degrees, which is darn close to 60 degrees. And what do we say a 60 degree was? Root 3 over 2. And that's approximately 0.87. That, I guess, is just a little smaller. So, you know, maybe 0.83, something like that. But at least we start to get, I'll put 0.84 here. So I think I remember doing that once before. That's a little closer. All right. And what happens when we're straight up? Well, you know, we keep drawing triangles, and I guess we go up to a height of 1, where the opposite side folds onto the hypotenuse, and it's a 1-to-1 ratio. Here it's a 0.84 to 1 ratio. And at the beginning, there's no height. There is no height. So we're kind of like at the what? The midline. And I hope you understand that what comes after 3 is not going to be called 3.14. We're going to say pi. That's an exact value in our measurements. Always strange to think of a number that goes on forever as exact values. All right, so this is angles. The biggest we get is 1, the smallest we get is -1. I hope that explains why this function only kicks out numbers as big as 1 and as small as -1 and everything in between. So what's our range? 7 plus 9, 16, 7 minus 7 plus 9, 2. Right, so we're just continuing the conversations. Now, I hope you, after I talk about this, understand why we've been doing some of the things we've been doing in the order we've been doing them in. All right, our goal here is to be able to look at this, and I'm looking at it now, and I'm seeing centers at -5, +3, 1 by 9, 34, and radius is 7. I think that took about 10 seconds, and that's our goal. Be able to look at something like this and understand that. That's a deep understanding. Where did it come from? X plus 5 squared minus 25. I hope that looks familiar. Plus y, where am I? Y minus 3 squared minus 9 equals 15. That can be x plus 5 squared plus y minus 3 squared equals 49, which I'm going to write as 7 squared. What were we doing in the last problem? Put triangles in a circle? Well, here's a triangle for you. Guess what that area is? X plus 5 squared. Y minus 3 squared. 7 squared. Now, as this gets, the altitude gets smaller, that implies that this has to get bigger. As this square area gets smaller, this one's got to get bigger because that's constant. And you get this rotation, this possible rotation. Let's look at this from the standpoint of a test question. Name a couple of coordinates, right? This is no different than the standard form for a line in terms of usage. Make that 0, y could be plus or minus 5. So y could be +5, y could be -5. Make that 0, x could be 5. X could be -5. What's the center? Sure looks like it's 0, 0. So what makes 0, 0 here? -5, 3. That's the center of this. And instead of going 5 units that way, in fact, I could make another triangle here, huh? This is a famous one. What's that one? Well, that's 3 and that's 4 and that's 5. 3, 4, 5's in there and all the positive and negative. So this won't be too hard for you. I bet students have a lot of success with this pretty quickly. First time you hear anything, it's probably, oh, what am I looking at? But with a day or two of practice, given what we've done with completing the square work, that should come to you pretty easily. Okay, let's move over to bounded area. That's the reason I'm doing this 11 through 21 problems, because I butchered this yesterday. I had to delete a video. My God, I get to the point where I'm talking, thinking about what I want to say and not looking at the numbers carefully. Botching, getting old. Nursing home 6 miles up the road though, so I'm in good shape. All right, so why am I doing this now? Because when kids come into my calculus class, they can't graph these things and they can't find the points of intersection. That's the whole purposes of our courses right now, is to give you those foundational skills so that when you get to calculus, you can interpret what we're doing and see, I hope, the benefit of the whole study. And then, well, this is grandma driving on Route 91. I already told you this before, but she's driving on Route 91. These are rates, grandpa's chasing her maybe, and maybe this is her rate, but if we know her rate at which she's traveling and we can figure out a time of the day and where she was on the road, we can go out and help her out because her driving skills are pretty weak. And so that's where we're headed with this stuff, to save grandma. If anybody ever asks you why you study math, that's why. Okay. So, bounded area, stumbling block, let's draw x squared. You need to know how to do that. Let's graph x plus 6. 0, 6, up 1, over 1. Boom. All right, so here's your bounded area, enclosed. And that's going to tell you stuff down the road. It's going to give you information. I'm not going to talk about it more than that at this moment. But what's important here? The ability to graph those two things and also find their points of intersection. Their points of intersection. Oh, points of intersection, I guess, is where equations equal each other. And we've been practicing this skill, and not enough. Not enough, trying to get everything in front of us, but this should have been practiced almost ad nauseum in the Algebra 1 level. Quadratics, we set them to 0. We factor if possible. X minus 3, x plus 2 gets the job done. And we don't forget to say equals 0, and we don't forget to say that there are two x values. This one is 3. 3 squared is 9, 3 plus 6 is 9. We don't care about the 9 right now. We're just looking at the 3. And over here, this one is -2. -2 squared is 4. -2 plus 6 is 4. And we don't care about the 4 right now. What we have is -2 to 3. And in calculus, you will learn to do -2 to 3. Top minus bottom function, top function, x plus 6. Minus the bottom function gets us 1 altitude. That gets an exact area. But I'll be asking you to draw these things and label those points of intersection. Okay? And the calculus of this part of the calculation is the easiest part. Understanding integration, that's another matter. Right? But unless you can have the foundational skills, then you're not going to get to hear the conversations about what integration is, because you're going to be worried about how to graph this thing and can't do it. Okay, so you got to learn it now. All right, so we'll be putting one of those on every test at the end, at the bottom of the, on the answer key. You'll get to draw some pictures. We all like drawing. It's fun. All right, next is I need an eraser. Okay, hopefully I said everything I wanted to say about this problem, because it's going bye-bye. All right, algebraic fractions. How do we put those together quickly and easily? That's our goal. And we'll check it today too. And before we do, let's go to basics, stuff you studied in grade school. Yep, 1/2 plus 1/3. This is what we were taught. 3/3, 2/2, common denominator, put them together. Yeah. Let's see if we can speed that up a little bit. All right, let's get rid of the middle work. Let's just look at the, I erased too much there. I can read it. 1/2 plus 1/3 equals 1 times 3 plus 2 times 1 over 2 times 3. I think that's what 3 plus 2 over 6 came from. Now, can I see 1 times 3? Bingo. Can I see 2 times 1? Bango. Can I see 2 times 3? Bongo. It's that simple. All right, so let's go back over here. And this is not my trick. This is a mentor of mine. Said bingo, bango, bongo many years ago. And I think it's very useful. So I'm adopting it. And I hope that if you find things useful in your classes, that you adopt those as well. All right, so first step, and this is a very important step, and you can shortcut it down the road, but not right now. Bingo. I'm subtracting. Bango. Bongo. For the time being, use parentheses as kind of a mold. So what's bingo? Numerator times denominator. 3y minus 4 times 4, which is 12y minus 16. Then, bango. Denominator times numerator. 5 times y minus 2. 5y minus 10. Notice. And unless you put the parentheses there, my experience has been you'll continue to make mistakes for weeks unless you're really looking critically at your answer keys, and not everybody does. 5 times 4 is 20. From there, you should be home free. So what does this equal? That's 20. Okay, 12y minus 5y, 7y, minus 16 plus 10, minus 6. I'm looking at y equals 1 as a very friendly number. I put y equals 1, well, that wasn't very difficult. I get 1 over 20. And over here, if I let y equals 1, I get 3 minus 1/5. And y equals 1, I'm getting 1 minus 1/5 minus negative 1/4. Okay, and that becomes minus 1 times minus 4 is minus 4. Minus, let's put the parentheses over here, minus 1 times 5, there's bingo, bango, bongo. Okay, and minus a minus is positive 5. 5 minus 4 over 20 is 1 over 20. The left side's 1 over 20, the right side's 1 over 20. It's not a formal proof, but it's a way to make sure you don't make a careless error if you got extra time on a test. Algebra is supposed to be true for any number. So I tried a number. It's true. All right, moving along. And we reduce fractions. We reduce them all the time, but sometimes we use inappropriate language, and I'm guilty of it too. 4 divided by 4 cancels. No, it doesn't cancel. It really equals the number 1, which then gets multiplied into the problem and not shown. And sometimes students do something like this. They say that 10 divided by, what do? They say 10 divided by 4, the original problem, is equal to 6 because they cancel the 4s. Can't do that. Division does not undo addition. You can divide out the 4s and create the number 1, provided it's a multiplication statement. Just say that because some folks make that mistake. All right, so back to here. What's the way to simplify a fraction, to reduce it? Writing products. That's a product. So over here, if we're going to reduce this, we got to be able to write products. And we've been practicing that. What's another way of writing the numerator? Take out what's common. 3x times x plus 3. That's what we've been practicing. Now we're taking it to a slightly higher level. What's x squared minus 9? I usually say x plus 3, x minus 3, but I'm going to do x minus 3 times x plus 3 this time. Reverse the order, commutative property multiplication. And I can divide out the x plus 3's. That becomes the number 1. And that's 1 times 3x is 3x over x minus 3. So what would be a good number to plug in here? I think 1 again. 3 over minus 2. Maybe I should make the number 2. 3 times 2 is 6. 2 minus 3 is negative 1. So negative 6 when I let x equal 2. So over here, I better get negative 6 when I put a 2 in. That's 12 plus 18 divided by minus 5. Ooh. Oh, yeah, that's negative 6. That's 30 divided by negative 5. Ooh. Oh, good. So glad. And what happens if those fractions get more complicated? Well, we take the same tack. We approach it the same way. We factor 3 times x plus 2. Writing products is where you're going to get your practice in the second half. That's why we didn't do a whole lot in the first half. Covered all the material. Now it's time to have a little more fun with it. I'm going to take a little liberty and I'm going to multiply by the reciprocal. You're supposed to know that anyway. So x times x minus 4. And then we've got our 2x and x situation, right? We probably have clues here somewhere. It's probably an x plus 2 in here. So I'll just throw it in there. These are internet problems. So I'm just assuming x plus 2 will divide out of the problem. So that's 2 times 2 is 4. And I need another 5. Well, there they are. That gets me up to 9. All right, so it looks like x minus 4 becomes the number 1, which multiplies times x and disappears, hiding their x plus 2. That divides out to be the number 1, and 1 times 3 disappears. And so I'm left with, looks like 3x over 2x plus 5, and I'm moving on. But if I had a lot of time on a final exam, I might put in a number. I don't know what number I pick. I think I'd pick 4, 5. I'd pick a 5. I like a 5. That would have given me 15 over 15, which is equal to 1. Then when I put a 5 in here, I better get a 1. But being a little silly here. Okay, need a coffee. All right, what's next? Compound interest. Oh, yes. The limit as x goes to infinity, 1 plus 1 over x to the x. Yes, I don't know why I'm doing that. Don't worry about it. This is called the principal, not the principal of a school. No. But what you put into the bank, and A is the amount over time. I should put A of t. Why don't we do A of t, amount of money over time that you get from your savings account that is being compounded continuously at a rate of, all right, let's do 4%. Okay, so our goal is to be able to do that calculation right now, which is 0.04 into 0.7, which can be multiplied by 100, which makes it 70 over 4, which makes it 15, 16, 17 and a half. So it would take you 17 and a half years to double your money. All right, let's show you where that comes from. Let's start with $50. E, 4% is 4 divided by 100, right? 4 divided by 100 is 0.04 T. And we want to double our money, so we want to get $100. See how long it takes. So first step, divide by 2. E to the 0.04 T. And we've been learning how to solve the equations, and some of you have it down pat. So nice. Ln of 2. E, I'm sorry, 0.04 T. And some of you at this line of work may have said, hey, that's got to equal 0.7. That's got to equal 0.7. E to the 0.7 is 2. Great. This is formal. In case you don't have a number that you know. All right, so that brings us to what? What I had over here. What I had over here really was ln of 2 divided by 0.04. We want to be able to do these enough to get there, and my experience has been 3 or 4 days. Max, for most folks. If you're paying attention, if you're looking at it. 11 pi over 3. Our goal is to be able to look at that and say, okay, 12 pi over 3, I'm at 11, I want to get a half. We want to be able to do all those drawings in our head by May 15th. Right now, we're just getting up and running. So how do we do it? Pi, top half of the circle. Break it up into 3 parts. Oh, yes, draw those triangles, and we know we're looking at 60-degree reference angles. I want 11 of them. Well, I know this breaks it up into 6. And I know if I go around again, that's 12. And I want to be at 11, which means I'm down here, 1 less, because we go this way, right? And so I'm right here, bring it up to the x-axis, I create a right triangle, and cosine is the width. You know the hypotenuse is 1, that never changes signs. There you go, there's your half. Okay, and there's introduction to the unit circle. If somebody's just starting to look at this material, introduction to unit circle work. There's some lecturing going on there to get up and running with this. And so if that's the first time you've seen this, well, you got to go here. Right? And what is a radian? You got to look at that, or somebody's videos on what a radian is. Okay, can I get a question mark there? Okay. And I forgot to mention that the circle problem that we did before, the x squared plus 10x plus y squared, right? There's a lecture on that, running around in circles. All right. And you don't have to look at my stuff, but, you know, I did a little spoof on that one. I got a little bored, I think, and I got a little silly. I had fun with it, though. All right, so now we're looking at 19 pi over 6, and judging from what we did over here, you're looking for multiples of 6. Then you're trying to find out where on the circle, if I got it, where on the circle is a nice multiple of 6. I'll look at it with you. 18, so minus 18 pi over 6 is what comes to mind, which is minus 3 pi, yes? Okay, and this is going in the other direction. Instead of counterclockwise, we're going clockwise. We're starting at 0. Radius, length measurements, terrible circle, but that's okay. Good enough. So once is negative 2 pi, negative 3 is over here. We're going a little further. Pi over 6 is 30 degrees, and we're looking at that height, and that height is above the x-axis, so there's a half. And then we're going to add one more trig ratio. I don't even think I have to define it. All I got to do is show you the triangle and the answer, and you'll probably know what to do with it. 3, 4, 5. What's the tangent of angle A? 4 to 3. So what's the definition of tangent? Opposite over adjacent. The opposite side divided by the adjacent side. And if we wanted to make this a unit circle, which has got its benefits, you know, and we've got just a smaller triangle with the same ratios. It's one of the traits of trigonometry, one of the truthful aspects of the study. The ratios don't change. 4/5 to 1 is, 4/5 to 3/5. Sorry, I'm so used to doing sine and cosine. 4/5 divided by 3/5. Well, you can just slash the 5s, right? You can take them right out of the picture of the problem, because 4/5 divided by 3/5 is the same as multiplying by its reciprocal. I didn't take the reciprocal. And getting towards the end of the video, I really should slow down so I don't make an egregious mistake and have to do the video again like I did the last time. All right, so we got a new trig ratio, and the ones that I want you to get familiar with first are the pi over 4s. Then we've been doing pi over 3. We've been doing pi over 2. We've been doing pi over 6. I got to do that one a little lower. Smudge. And we've been doing 0. And if we want to talk about heights, then this is the square root of 0 over 2. This is the square root of 1 over 2. Pi over 4 happens to be the square root of 2 over 2. Pi over 3 is the square root of 3 over 2. And pi over 2 is the square root of 4 over 2. And we can kind of see heights 0, 1/2, root 2 over 2, root 3 over 2, root 4 over 2. 0.5, 0.71, 0.87, 1. Then we got to keep talking about those numbers. All right, so if we're looking at a 45-degree reference angle, 180 divided by 4, then that picture has to be true. Because if this is 45 and that's 90, then that's 45. And so those sides have to be equal, which means their Pythagorean relationships have to come out as being equal. So what is this length? The square root of a half. I've looked at it over here. So you've seen this before, but doesn't mean it's processed yet. So we look at it again. Square root of 1 I know is 1. And I can rationalize the square root of 2. And if you're looking at it, you should be able to follow it. And I'm asking you to memorize square root of 2 over 2, about 0.71. If you don't have a feeling for the numbers you're working with, you don't have a feeling for the calculation. So again, top half broken up into 4 parts. 4 even parts, 45, 90, 1, oh, my brain, 125, I guess. And 130, what is it? 90 plus 45. Woo! 135. And then we got ourselves our 150 and our 180. Oh, forget what I'm saying. 180 over here. 135 there. 90 there. 45 here. 0 here, if we're in degrees. Radians, pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. All right. Yeah, obviously my brain's getting a little tired here. So we want 7. So 1, 2, 3, 4, 5, 6, 7. There we are. And we want the tangent. So that's negative root 2 over 2. And that's positive root 2 over 2. And if I divide that by that, I get negative 1. Okay, I'm running out of breath. We're done. So there's another set of problems that we are going to be adding to our foundation. And we got a lot of time. And so there's no rush. There's no reason to panic. Just like everything else, you look at it the first time, you got to give your brain time to sort it out, come back, look at it a little bit next day, come back, look at it about day 3, things start to make a little sense, and day 4, bingo, bango, bongo. I'll see you in class in a couple of weeks.